Remember the good old days? You know, when the ice cream truck drove by every afternoon? When you could go outside and play in the sprinkler? And when your power and ground planes were just nice, simple DC constant voltages? Yeah, those days are gone. Now we have to work and commute and balance our bank accounts and pay our taxes, and our power delivery networks interact with our signals, all crushing our little nostalgic youthful souls. Okay, wait. It isn't all that bad. It turns out that there is help for your power integrity problems. Hi, I'm Amelia Dalton, host of Chalk Talk. Today I'll be talking to Todd Westerhoff of Mentor about power aware simulation. If we understand the physics at work in our PCBs and have the proper analysis tools, we can provide stable power for our devices while protecting our signal integrity with clean return paths. And of course, I'm still listening for that ice cream truck. Doo doo doo. And before we get started, don't forget to click that link. There you can find more information about understanding power-aware simulation from Mentor. Hi, Todd. Thank you so much for joining me.
Hi, Amelia. Thanks for having me.
Okay, Todd, I want to understand this power-aware simulation, so we better get started.
Okay, well, that's a great question. And at the outset, we should probably acknowledge that power aware is a term that's used differently by different people. So what we'll do is we'll give you our definition of it. And in our view, power aware simulation is a type of time domain simulation that's trying to account for interactions between high-speed signals and the system's PDN, the power delivery network, which is a distributed structure of the board, the package, and the die-level capacitance and power system. And what we're really trying to do is figure out how that power system is interacting with those signals and degrading system margin.
Okay, so you're talking about the importance of understanding these interactions. What are these interactions we're talking about specifically?
Before actually we even talk about those interactions, we should talk about what a power delivery network actually does, because it's really important to understand that a PDN actually has two purposes. Most of the time we think, well, a PDN delivers power to the parts, right? And that's all it does. But it actually does one other thing that's critically important, and that is that it provides the controlled impedance path that the signals propagate over. So when I have a 50 ohm driver and it tries to go out of the package and onto the board and into another device, it's important that we maintain that electrical environment, that characteristic impedance through that whole path. And the PDN is actually, because it's the reference planes and it's where the return current for the signal is actually propagating, it's critically important to understand that the PDN is actually responsible for signal propagation behavior as much as it is delivering power to components. And so the point that goes with that is that if we don't design the PDN correctly, what we're going to get is these unwanted interactions between signals and the power delivery network. And what that is going to end up doing is degrading signal margin. Now, it turns out there are three specific phenomena, at least in Mentor's view, that we talk about. We talk about simultaneous switching noise, we talk about coupling between vias in the power cavity, and we talk about the behavior of signals that have non-ideal return paths, all as contributing to the degradation of system margin.
Okay, cool. Can we get a closer look at these three?
Okay, so let's do that. So we enumerated three key effects that are going to interact or degrade system margin. One of them is simultaneous switching noise. The other is via-to-via coupling. And finally, the behavior of signals that have return paths that have disruptions in them, causing non-ideal return path behavior.
All right, let's take a look at each of these in more detail. So let's start with SSN.
Okay, so simultaneous switching noise is related to simultaneous switching outputs. They're companion terms. If you have a bunch of device outputs and they're all switching at the same time, each device output on its own is going to demand power from the power rail in order to drive the output. And if I get a whole bunch of them switching at the same time, that demand for current is actually being magnified. So you have multiple outputs switching simultaneously, simultaneous switching outputs, or SSO, creating this demand for current that actually causes fluctuations on the supply rail called simultaneous switching noise, or SSN. And it's an output behavior-driven phenomenon. It's dependent on the pattern. So if I have an 8-bit bus or a 16-bit bus and I suddenly go from all 0 to all 1, then what I've done is I've maximized the demand for current from the power rail. And if I have things just sort of randomly switching up and down, but they're not switching in unison, then I have lower average demand for power. So the point with SSN is it's very pattern dependent, and we can use specific patterns to sort of exacerbate that demand for current and aggravate the problem. Now, just by way of demonstrating this, let's take a look at a simple example. And this obviously isn't a real circuit, right? It's just meant to demonstrate the phenomenon. So we take a device that has a collection of outputs, and we're going to switch them all together. We're going to deliberately cause noise in the power supply by putting an inductor between the power rail and the device. Now, that's obviously kind of kooky, right? You would never really do that. But again, it demonstrates the behavior very clearly. And the reality is we do have inductances in our power rail in a real system. And so what we'll do is we'll put resistors on the outputs so that we can sort of create this demand for power, see how the noise on the power rail affects the output behavior, and then we can observe those outputs directly because they're connected to resistors. Now, if we simply switch one bit, so we sort of have the minimal demand for current, if you want to think of it that way, what you've got here is you've got the switching output in green, and that's a relatively clear waveform. Looks a little funky perhaps, but that's actually the nominal behavior of that particular output. And then what we've got is we've got all of the other outputs that we've held low in yellow. Now, you'll notice that there's actually some noise there, which is interesting, right? Those outputs should be low, but that inductor is causing the power rail to bobble, and even on the low outputs, that's causing some noise there. And then finally, that red line, VIP2, that's actually the power supply rail. So that's as if we could go into the part and probe the power right at the output driver where it matters. That's the amount of noise that we're inducing on that power supply rail when we switch that single output. If we actually switch all bits at the same time, we've greatly magnified the demand for current. We're going to magnify the voltage drop across that inductor, and we're going to get a voltage droop at the power rail supplying the output. And you can see, actually now the whole thing just looks kind of funky, right? Instead of having a nice clean rising edge on our green output, which is the output of interest, it's got this very protracted rising edge behavior. We see the same thing on all of the other outputs because they're all switching the same way. But most importantly, look at the amount of noise we have in the red line, which is the power rail. So what this is showing is exactly what we said before, that simultaneous switching noise is pattern dependent. Certain patterns create more noise than others.
Okay, Todd, so what about via to via?
Sure. So let's take a look at via-to-via coupling. What ends up happening is that when I have a trace routed on a board and it changes layers through vias, what's happening is before I go through the via, the trace is going along the board, its return current is flowing in some reference plane underneath it. And then what happens is that that current goes through the board and goes to some other trace on a lower level of the board, for example, and there's a different reference plane that that return current is flowing on. And as that energy goes through the board, as that current goes through the board, it's actually going to create a magnetic field that's going to go sideways out through those planes. Think of it as sort of blowing energy into the cavity. Probably a poor visual image, but let's just stick with it for now. And so this current goes through the board, it's current, so it's going to create a magnetic field, and that magnetic field is going sideways in that cavity. And what happens is that that energy just sort of radially propagates out. And if there are any other vias in its path, some of that energy is going to couple into those vias and induce current. So we have signals that are basically just coupling through the power plane. Now, in this particular picture that we've got right here, this is sort of an interesting one because what's happening is that you've just got this one lone via and there's no connection. If those two green planes there were power planes, there's no connection to those planes in this particular image. And so you're going to maximize the size of the radial wave that's being propagated in that cavity. If instead what we do is we use a thing called a stitching via that's going to provide a direct electrical connection between those two planes, then what happens is that the return current that's flowing on the top plane now has a clean way to jump down to that bottom plane with the signal transition. And what we're going to end up doing is reducing the amount of energy that we basically put in that radial wave between those planes because all of that energy, or at least more of that energy, can flow through that stitching via. Now, one other minor note, and that is that the stitching via strategy works really well, but to directly connect two planes together, obviously they have to be the same voltage. Shorting power and ground is a bad idea. It tends to cause fires. And so if we've got planes that are different voltages, then we end up using decoupling capacitors to get that current from one plane to the other. But the problem with that is that those decoupling capacitors themselves have parasitic values, and then their inductances associated with the vias that mount them. And all of that limits the effectiveness of those things at high frequency.
And finally, what about non-ideal return paths?
The differentiation between via-to-via coupling and non-ideal return paths is honestly a little fuzzy. We're sort of creating an artificial distinction here, and some of what I'm about to talk about is similar to what I just said. But the idea is that whenever I have trace or current flowing in a trace, The reality is that the current just doesn't flow in the trace. It flows in the trace and it flows in the reference plane beneath it, right? Current flows in a loop, as we all learned. And so when a signal transitions from one layer to another in a board, or for that matter, if it's routed over a plane split and you've got this trace and it's referenced to one plane in one part of the board and then it goes over a split, it's referenced to a different, all of that return current that's being induced under the trace has to be able to form some kind of a continuous path. Basically, you have to get the current back to where it came from. And so there are a number of interesting examples for what happens with return paths and how they become non-ideal. This diagram here that we're looking at is actually showing a case where we're coming in on a top layer of a board. We're going across two different reference layers coming out on the bottom. So there's the return current on the top reference plane that had to get to the bottom reference plane. But then as you get to the right of that diagram, you can see that the reference plane is actually split, and we're going from one reference plane to another on that same trace on the bottom right there. And again, that return current has to jump from plane to plane. So this is an interesting illustration, sort of helps you visualize some of these things. What we'll do is we're going to take this trace that goes from the top of the board down to the bottom of the board, and then we're going to use the stitching via to channel the return current, all right? And we're going to try two different experiments. On the top left there, what we've got is this trace kind of coming from the top left, and then in the middle of the board, it goes to the lower layer and it goes down to the bottom right. And in the diagram on the left, there's a stitching via right next to the signal via. So the return current can transition from plane to plane right next to the signal via, right? That's the ideal case. In the right diagram there, that stitching via is sitting over on that left leg there, right? And so it's a good distance electrically. It's a really good distance away from where the signal via is. And what we want to see is what happens to the behavior of the signal when we take the stitching via and move it far away from where the signal via is. So the next slide, what this does is it shows us the return current. So this is a colorized diagram. The blue is absence of return current. The green is actually the presence of return current, in red, which is directly under the image of that trace. That's where you have your maximum return current. And so if you look on the left, what you can see is that when the stitching via is right next to the signal via, the return current flows pretty much right under the trace, just what you would expect. But on the right, when the stitching via is well away, this funny thing happens, which is that the return current on the top has to flow all the way over to where that stitching via is, and then transition to the bottom layer and come all the way back and then pick up and run the trace. So if you thought of it sort of as like a waterfall diagram, right? You can imagine that there's literally water on that top plane, draining through that hole and going to the bottom and then coming around. And so the important point here is that when I have a signal flowing over a plane, that return current is just as important as what we think of as the signal itself. Really, the signal is the combination of the trace and the return plane or the return path. And it doesn't matter whether I interrupt the electrical trace itself or whether I interrupt the plane beneath it, either one is going to end up affecting the signal. And most of the time, we just sort of pretend that these planes are perfect and we don't have to worry about this stuff, but that's not what really happens.
Okay, so I think I understand what you're saying about the return path, but how does that affect the behavior of the signal itself?
Excellent question, right? Because let's go back to what we just said, which was that it doesn't really matter whether our disruption is in the trace or in the plane beneath it. Either one is going to disrupt the signal because the signal is really the sum of both. And so what we've got here is we've plotted a step response to the case where we have our ideal stitching via and we have our stitching via located far away. The green is the ideal case, and you just got like a nice clean step response there. But look at the yellow one, it rings like mad. And that's because what's happening is that energy is just sort of banging back and forth between those planes. All right. What's really interesting, it's beyond my capability for math, but you'll notice there's a periodicity there. You can see actually that thing ringing and damping out. And if you were, persistent enough, you could actually infer something about the physical size of the structure just from the period of that ringing. And so this is another really interesting case when we look here. The case of the stitching via being artificially far away, okay, that's a science experiment for demonstrating things, right? We don't really do that except by terrible accident. But one of the things that happens all the time is the idea that we have too few stitching vias to return the current that we need, right? When we look at the boards that we're designing right now, we're always pin limited. We don't have enough pins. And as we said, our power delivery network actually has two purposes. One is it's trying to get power to parts. The other thing is it's trying to provide the reference for the signals that they propagate from chip to chip. And we never want to put enough ground pins on our components and things because we'd rather use that space for signals or something else. And so we're always sort of trying to figure out can we get away with a few fewer ground pins because, we can use that space for something else. But the problem is that when we start overloading ground pins, then what happens is we get this phenomena called return path sharing, right? So if you look at this, it's a little hard to see in the diagram, but what we've got is we've got 4 signals running and they're going from top to bottom of the board, and there are 4 parallel traces, but there's only one stitching via. So I've got 4 nice parallel paths for the signal itself or for the trace, but all of the return current has to get muddled together and go through that one stitching via together. And what ends up happening is that the signals actually combine or crosstalk through that shared stitching via, right? So normally we'd think, well, the signals are fine. They have their spacing or whatever. They're far enough apart from one another. We shouldn't really see crosstalk. But remember, it doesn't matter whether you mess up the signal or the return current. The effect is the same. So because we force all of those return currents to be shared through that stitching via, those signals actually couple through the return path through that stitching via. And you can see here's the case where we have these 4 signals that should just be this nice clean step response, but we're getting all these noise induced on them because they're actually coupling through that return via. And that's actually a real phenomenon. That happens all the time on boards simply because we typically don't want to put enough ground pins to allow all these things to isolate the way that they should. And then one last thing we wanted to talk about. This is one of those things that everybody thinks of as a no-no, right? You should never do this, but sometimes you just have to. Right? So we talk about a trace wanting to have a reference plane underneath it to maintain a constant impedance. And obviously, you don't want to switch planes. You don't want to go from one plane to another because, first of all, when the trace isn't over a plane at all, that area where there's that little black stripe because you're between planes, well, you don't have a reference. But then the other thing is that return current has to jump from one plane to the other. And if I don't put some vehicle for it to do it, it's going to create this large discontinuity in the return path. The reality is, particularly in some of our high-volume, cost-constrained devices, they're just not big enough. And we've got multiple power requirements and whatnot. We can't avoid doing these things, all right? So what we need to do is we need to have a reliable mechanism for figuring out if we have a trace going over a plane split, how do we effectively decouple those 2 planes, like with a capacitor, and quantitatively determine what the degradation of the signal is so that we know that, in fact, this design will actually work. So, we can't idealize it, or more importantly, we can't make it perfect by avoiding the split. We can't idealize it and pretend it's not there, but it's also fairly difficult to model it accurately and predict it. So how do we get there? So what we've talked about here are 3 different mechanisms for how power delivery networks interact with high-speed signals: simultaneous switching noise, via coupling through power cavities, and the effect of non-ideal return paths. The single most important thing to understand is all of these things can only degrade system margin. They close our eyes down. They give us less voltage margin, less timing margin. They never make it better. They only make it worse.
Okay, cool. Now that we all understand the physical effects, how can we include these in our simulations?
Excellent question. I tell you what, before we get into how we actually model things for power-aware simulation, let's take a step back because I want to talk about how we traditionally and typically do signal and power integrity and the assumptions that are baked into those analyses that we may not be aware of. Now, most of the time what we do is we think of SI and we think of PI, but we don't necessarily think of the two together. So we think about signal integrity simulations and we run analysis. We plot eye diagrams like you see on the top right there, and we look for eye opening, and we often compare the eye opening to a mask. So what we typically do is we do an independent power integrity analysis where we look at our components and say, these components have these power requirements. I have to have a power supply impedance that's no more than this over this frequency range. And I'm going to go and I'm going to look at my board and I'm going to put my decoupling capacitors down and design my whole power delivery network at the board and system level so that I meet impedance targets at specific places. But the important point there is that those 2 sets of analyses are disconnected. I'm looking at power as though I can meet an impedance target, and that's good enough. I'm looking at signal integrity as though I can just get an eye diagram with a particular opening, and that's good enough. And I'm not necessarily understanding the assumptions that are baked into that method of analysis.
Cool. Can we look at an example?
By way of analysis, let's take a look at this. Let's look at a really simple SI analysis. I like to break things down, just into their very basic pieces and then build back up. So I don't know how you get any simpler than this, right? We have a driver going through a via connected to a receiver, and then we've got a length of trace in and out of the vias. That's about as simple as it gets. We've got a part and transmission lines in a via. If we start to dig into these different elements, what we'll typically do for the driver and the receiver is we'll have an IBIS model. And IBIS models are these table-driven models of switching behavior. But the thing that most people don't stop to think about is that the model as it's typically used assumes that the connection to the power rail and the ground rail is perfect. Right? My power rail is stable DC to daylight. It never varies. We might vary it for voltage for what we think of as slow and fast, but there's no impedance component to that, and it never varies no matter how many or how few outputs we have switching. So you could say that the power delivery network, from the standpoint of IBIS models and even SPICE models with typical signal integrity analysis, is considered to be perfect. If we look at the transmission line, most of the time when we run our simulators, what we've got is we've got these 2D models of transmission lines. We're used to seeing sort of these field plots like you see on the bottom right there, showing the electric and magnetic field. And what those models do is they make the assumption that the return path under the plane is perfect and constant. It never varies. We might have a trace that has different widths and whatnot, so we're field solving different parts of it independently. Key point there, those models are really always making the assumption that the return path is essentially perfect. If we look at the VIA models are interesting. Like, I've been doing this for 20 years, and I didn't really internalize a lot of the idealized assumptions that are made with most VIA models until I actually started preparing the material for this webinar and this particular release. And so what will happen a lot of times is we have a VIA model. We know that's a cylindrical structure through the center of the board, and we'll look at the veer barrel and we'll look at the antipad and the planes beyond it. But when you really dig into it, and really every signal integrity tool makes this same assumption at base, what they really do is they look at it and they go, okay, we're going to treat this as a coaxial cable. We've got the center conductor, and then at the edge of the antipad, we've got the planes, and we're going to pretend that there's just metal going from plane to plane there so that we have a perfect coaxial cable. Except for the fact that you don't. It's not a coaxial cable, right? Those planes are isolated from plane to plane. And so we do this because it's easy to solve. It's a reasonably accurate model for a lot of cases for VIA. It's very easy to solve and create numerically and simulate. And what will happen sometimes is that they'll take these models, if you look on the bottom right there, and we'll divide them up. We'll give them more granularity. We'll say, well, we've got pads and antipads, and we've got different layers, so we'll break it up into smaller models. But from a return path perspective, we're still treating them as idealized. And again, we do it because it's reasonably accurate, and it's fast, and it's easy. And there are lots of good reasons to be doing that. But it's important to understand that you're really building these VIA models with the unstated assumption that there are enough stitching vias nearby to meet your every need. And if, in fact, you don't have a good return path from plane to plane, then these assumptions are being violated.
Okay, wait a minute, Todd. First you told me that all of these interactions were important, and then you tell me that people are ignoring them. So why would anyone want to run simulations with an idealized PDN?
It seems like a wonderful paradox, doesn't it? There are a couple of points, right? Number one is that remember what we said about these three forms of interaction. All they ever do is degrade system margin. Now, the fact is that modeling something with an ideal PDN is quick and easy. It's less detail in the model, the simulations run faster, things really become truly interactive. From a design standpoint, what do I really do? I start sketching things out broadly, and then I paint more and more detail in as I go. Everybody does that. Painters do that, right? They sketch stuff out and then they work the detail in as the painting progresses. The same thing is true in a digital design. I start by about how long can my lines be? How am I going to terminate? How am I going to set my drive strengths and all those things? And what does my trace spacing want to be? And I dial more and more detail into my design and my analysis over time. When we look at this whole thing about signal PDN interaction, there's one thing that's really simple, and that is that these interactions only ever degrade system margin. So from a system design point of view, if I'm creating something that doesn't work with a perfect PDN, then there's no way it's going to work with a real PDN. So why not, early in the design cycle, make that assumption that everything is perfect and only bring that into play as I get my design refined to the point where I really want to go look at that level of detail. And so that's what power-aware simulation is. It's the analysis in the time domain of both the signals and the power delivery network and how they interact so that we can account for the effect of those three different phenomena that we talked about.
All right. So what exactly does that process look like in your tool?
So in HyperLynx, one of the most important things about power-aware simulation is it's not an event, it's a flow. And we talk about a staged process of doing the things that we talked about. We first do signal integrity analysis with an idealized PDN because it's quick and easy. We rough things in. We bring more detail into the design in stages. We look at the individual nets, then we look at the nets with proper termination, then we look with crosstalk and so on. We do the power supply analysis or the PDN design the way we talked about at the outset, where first, we just sort of figure, here are the impedance targets that we want to meet and the parts of the board where we want to meet them. We do the traditional types of PI analysis. So we're going to do our SI the traditional way. We're going to do our PI the traditional way. Then we're going to bring the two of them together because this now becomes more of a detailed verification, if you want to think of it that way. And so we're trying to dial in the effects of simultaneous switching noise, via-to-via coupling, and the effects of non-ideal return paths, and see whether they're degrading the system margin to the point where it's not going to work, or we have to change something, or whether we're okay. When we look at how we model those interactions, because that becomes the key point, right? We talked about these three different interactions between signals and the PDN. How do we actually model those things? Well, we have to have a PDN model. We have to know how we're delivering power to the supply pins on the chips and what those frequency characteristics are. We have to have a model of the signal-to-signal coupling through the power cavity. And then sometimes what we actually do is we create a grander model that has everything in one piece. But what we do is first we run these 3D electromagnetic simulations to create these coupling models, and then we bring those coupling models into our simulation netlist and then run a simulation to show us how they affect design margin. Now, one of the interesting things that happens here is that even here, there are different trade-offs. We always tend to think, well, you just want to turn the accuracy knob all the way to the right. I mean, after all, it's only a computer, right? Why don't we just let it work harder? What do we care? And I think that tends to be a mindset of a lot of people in simulation is just crank the accuracy knob all the way to the right and we're good. The reality is there are lots of good reasons to use different settings on that knob. Most of the time, when I crank the detail knob all the way to the right, my electromagnetic solution time goes way up, my simulation time goes up, my throughput goes way down, my ability to meet schedule goes down. And the fact is, a lot of times you don't need it. So one of the things that we try to do is allow people to meet different points of this trade-off between detail and time. Whenever I create a more detailed model, it's going to take longer to create. It's going to take longer for me to make sure it actually was correct, even though arguably it should always just be automatically correct. And it's going to take longer to simulate. And so one of the things that we do in this stage is that we give people sort of different trade-offs between detail and throughput so that they can pick the right trade-off based on their design and what they're trying to get done at that point.
Now, Todd, I don't want to go in and do this all step by step. That sounds like a lot of work to get through.
That's absolutely true. You know, there's a lot here, right? There's a lot of detail here. And one of the challenges with tools like this is always, how do you get people through it? Because there's all of this technological complexity. But at the end of the day, people just want to go get a job done. So, you know, we call them wizards, but I think of them as sort of an automated workflow. And broadly speaking, I just sort of talk about it this way. If you're going to go fly a plane, Boeing 777, flying the plane manually is fairly complicated. There's a lot of controls and knobs and dials in that thing. Flying it on autopilot is arguably a lot simpler, right? I plug in the destination and some parameters and the plane flies itself. You can still fly the plane manually because all of that capability is there, but the autopilot is trying to take much of that complexity away from you. So in the HyperLynx world, what we do is first we create all of the capability that lets you do whatever this technological task is. It's sort of, you know, the manual method, if you want to think that. We start by how do we attack the problem? What's all of the simulation functionality and data integration that has to happen? And then what we do is we lay a wizard on top of that, which is sort of stepping you through that process. So the goal of the wizard is just to walk you through a standard flow so that you don't have to remember all the dance steps yourself. It's going to guide you on the dance floor, and it's going to prompt you for all the information that you need to do. You can still go do all this stuff, you know, the way everybody else does, step by step if you want to, or more importantly, you can step outside the wizard if there's specific tasks that you need to accomplish. But generally speaking, you're just going to follow the flow. And you know, this is an example just of what that flow looks like. It tends to guide you step by step through different phases of a process, prompt you for whatever information it needs to perform the analysis at hand, and then at the end, it'll go run the simulation and present results.
So what do the results of this simulation look like?
So there's a lot of things that come out of simulation, but typically, particularly if we're looking at something like DDR, we're looking at eye diagrams, right? And we're looking for eye opening because typically we've got some eye mask that says that at the receiver, the eye has to have at least this much width and at this much height in order for us to adequately receive that signal. And typically what we'll do is we'll apply that eye mask to a measured eye or a simulated eye, and then we'll measure margin in terms of voltage in the vertical dimension and timing in the horizontal dimension. So here's sort of like a baseline analysis, right? So we run that wizard I talked about. We idealize the PDN, right? So we just make it ideal. It's typical standard analysis. And then what we do is we look at how much margin do we have vertically and horizontally for, how good are we? Then the next step that we do is we'll take the PDN, we'll model the real PDN. We'll extract the models for how we supply power to the parts and how we get from chip to chip. And then what we'll do is, because we have a real PDN there, is we remember all of these effects are data pattern dependent. So it depends on how many bits am I switching and what pattern am I switching them with. Like switching all 0 to all 1 is going to create like maximum noise on a driver power rail. And so here's a case now where let's just switch one bit. We'll model the real PDN and we'll model one bit. And if we step back for a minute, you can see that eye actually got a little bit taller and smaller. You can see the signals are getting a little fuzzier, right? You can see that they're beginning to close in a little bit. And so, okay, that's interesting, right? That even with one bit, when we brought the real PDN there was enough inductance, just even at the base level, that it caused the height of that eye to collapse a little bit. If we literally go switch everything, now we see two things. Number one, it's gotten smaller, and we could look at all of the detailed numbers. You can see it's gotten demonstrably fuzzier, right? The reality is it's not too bad. There's still plenty of margin here, right? This design's going to work just fine, but we can see how the signal is degrading or how the design margins are degrading with additional numbers of bits switching. Now, in this case, again, we're good. We're okay. We can go ahead and let this one go. But different designs would have different behaviors. The other thing that is really interesting here is that this kind of analysis allows me to sort of violate some of these coveted rules of thumb. So very often what will happen is that if I'm trying to design a high-speed system and I've got ground reference data nets, we're just going to say, well, you got to be ground reference from beginning to end. You can't change the reference voltage on any of the nets because we can't afford the inductance for the return path to go from plane to plane. And very often people will try to do that. And they're increasing their cost of the design sometimes because they're trying to put additional planes into the design and they're making their stack up bigger. They're making their board more costly. We're seeing the consumerization or the electronification of everything. So, what are we trying to do? We're trying to make boards smaller. We're trying to make boards cheaper. That means that we have to take some of these rules of thumb that we've lived by and start violating them. And then we need to be able to quantify the effects of violating those rules because ultimately that's going to allow us to reduce our product cost. This is the type of analysis that will allow us to do those types of things.
Very cool. Now, Todd, this has been a lot to take in today. So can you recap your main points for me?
Yeah, there's a lot here. It's an interesting subject. There's just really a lot to get into here. But, at the various highest level, I think that the three important things are that high-speed signals and power delivery networks interact. And we don't want them to, but they do. And when they interact, they only ever degrade timing margins and voltage margins. That's all they ever do. And it's critically important to be able to assess that and quantify it. It's also important to look back at the way that we've traditionally done SI and PI and realize that we've treated SI and PI as separate tasks, and therefore we've neglected most of those interactions. And therefore we don't typically have good ways to quantify them. And ultimately, what we're trying to do with HyperLynx, or what we have done with HyperLynx and power analysis, is give somebody one environment where we can do SI, PI, and power-aware simulation to deliberately and quantitatively quantify those effects.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Todd. It was a pleasure speaking with you.
Thank you. Thank you for your time.
And before we go, don't forget to click that link. There you can find more information about understanding power-aware simulation from Mentor. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out the Chalk Talk section of EE Journal. Can't miss it, right across the top. Or head on over to YouTube. Keyword EE Journal.